Hello! In this video we're going to do an intro to logarithms. So before we get started talking about logarithms, I just want to kind of orient the conversation. Just recall a couple of basic math facts. Addition and subtraction are inverses of each other. That's pretty basic. So if I had something like x plus 3 equals 9, and I wanted to solve for x, we do the inverse of plus 3, which is subtract 3. And you end up with something like x equals 6. Multiplication and division are also inverses of each other. So if I had like 4x equals 7, and I wanted to solve for x, I would do the inverse of multiplication, which is division. So I know this is extremely basic, but I just want to get us thinking about inverses. Another type of inverse we should be familiar with is that exponents and roots are inverse. So if I had x cubed equals 12, and I wanted to solve for x, I would do the inverse of the cube, which is the cubed root, to both sides. So I would end up with x equals the cubed root of 12. So what happens if we want to solve for x, but x is in the exponent itself? So something like 2 to the x equals, let's do 6. If I wanted to solve for x, i.e. if I wanted to get x by itself on one side, you might think, okay, well maybe we can take like the x root of both sides. So the x root would give us 2 equals the x root of 6. Well, that doesn't really help us get x by itself on one side. So this approach is not working. If I have an x in my exponent and I want to solve for x, we have to use something called logarithms. Logarithms and exponentials are inverses of each other, in the same way that addition and subtraction are inverses of each other. They're basically opposites. They undo each other. So here's a rule. Logarithms and exponentials can be converted back and forth, and I use this little mnemonic device. So here's how it works. If you start off with an expression like a equals b to the c, we can rewrite this as a logarithm that looks like log base b of a equals c. So this probably looks like a foreign language right now, but the way I remember how to convert these and what order our variables go in or what order our different pieces go in is ABC turns into log back. You can kind of see ABC turns into log back. Or it also works in reverse, of course. If you had a log base b of a equals c, you could convert that into a equals b to the c. So that would be log back turns into ABC. Now, one thing that's usually pretty easy to remember is that b is your base. So if we're writing it in exponential form, b is the base of your exponent. And if you're writing it in logarithmic form, b is the base of your log. So we would call this log base b of a equals c. So we're going to do a couple of quick examples where we convert something back and forth. So if I had, let's say, 9 equals 4 to the x, and I wanted to solve for x, I could convert this into a logarithm. So I would have log base 4 of 9 equals x. So this is the way that we can get x by itself on one side. This is how you, quote, solve for x. You convert your exponential into a logarithm. And the expression on the left, while this might look a little confusing, this is actually something that we can plug into a calculator. There are calculator buttons for logs, and you can type this into your calculator and you'll get some kind of a decimal number. So this is how you solve for x given an exponential. We can work these problems in the opposite direction as well. So let's say I had something like log base 2 of x equals 6, and I wanted to solve for x, we could convert it into an exponential, which would give us 6, nope, oh, it would give us, let's see, x is our a value, equals 2 to the 6th. And so you could then solve for x by simply multiplying 2 together 6 times. So x would be 64. So being able to convert back and forth between logarithms and exponentials is going to help you solve for x in a variety of situations. So there are going to be a few exponent rules that will come in handy when we're dealing with logarithms. So the first rule that will help us out quite a bit is if you ever have two equivalent bases like this. Let's say we have an equation where we have 2 to the x is equal to 2 to the 9th. Well, hopefully it's fairly easy to see that x has to be equal to 9. If 2 to the x equals 2 to the 9th, then these two exponents have to be the same thing. So essentially what you can do is just cancel these 2's out and you get x equals 9. So if you have two different exponents, but they have equivalent bases and they're set equal to each other, you can essentially just cancel out your bases. And this is a trick we'll use to speed up some of our problems. Another rule that's going to come in handy is involving logarithms. Let's say I had log base 2 of 2 equals x. If I were to convert this into an exponential, I would get 2 equals 2 to the x. Well, in this instance, x would have to be 1. 2 to the 1 equals 2 to the x, so x is equal to 1. What's happening here is this is canceling out. Log base 2 of 2 essentially cancels. And we can actually introduce a new rule. Log base a of a will cancel out and just be equal to 1. So this is a rule we're going to apply. The rule can get a little bit more complicated though. Let's say instead I had log base 2 of 2 cubed equals x. If I wanted to convert this into an exponential, my a value is 2 cubed, my b value is 2, and my c value is x. So in this instance, our 2's would essentially cancel and we would have x equals 3. So what's happening in this example of our logarithm is the log base 2 and the 2 are canceling each other out, and we're left with x equals 3. So let's refine our rule a little bit. If we had log base a of a to anything, so we'll say a to the r, the log base a and the a are going to cancel each other out, and this will just be equal to r. So this is a simplification rule that's going to help us in a lot of our logarithm problems. These two rules that I just outlined in red, you're going to want to commit to memory. Essentially, all you're remembering is that these cancel each other out, and these cancel each other out, leaving you with an r. All right, so it works kind of similarly when we're dealing with exponents. So if you have if you have a base taken to an exponent, but your exponent is a log of that same base, and we want to convert this, we'll say equals y. If we want to convert this into a logarithm, we would, so this is our, let me write this in a different order so it's easier to see. Y equals 2 to the log base 2 of x. So if we want to convert this into an exponential or into a logarithm, this is a equals b to the c. We would write log base b, which is 2, of a, which is y, equals c, which is the exponent, log base 2 of x. That's our exponent, log base 2 of x. Well, if you have log base 2 of y equals log base 2 of x, then necessarily x has to equal y. So what happens in this original problem, if we go back and look at where we started and where we ended up, the 2 to the log base 2 cancel each other out, and you end up with y equals x. So that brings us to a rule. A to the power of log base a of any number, so let's say x, will simplify just to x. So a to the log base a will cancel each other out, and you end up with just this x. So let's revisit exactly what's happening here. Just like addition and subtraction are inverses, so if I add 2 and then subtract 2, those things cancel out. Logs and exponents are inverses as well. So if we have a base of an exponent and a log with the same base, those two things are opposites of each other. So they are inverses, they cancel each other out, basically just bringing down whatever else is left. We'll get to apply a lot of these rules in examples, so if you feel a little bit confused right now, just bear with me. We'll jump into example 1. In example 1, we have log base 5 of 5 to the 7th equals c. We're going to do this problem two ways, the long way and the short way. So this is log back, this is our b, this is our a, and our c. If we wanted to convert this into an exponential, we would write a equals b to the c. So that would be 5 to the 7th equals 5 to the c. Well, this goes back to our first rule that we talked about. If you have two bases taken to two different exponents and they're equal to each other, 5 to the 7th is equal to 5 to the c, well, 7 and c have to be equal to each other. So we end up with 7 equals c. So c is just 7 here. That was kind of the long route to think about this problem, converting it, but we also sort of just learned a shortcut. Log base 5 of 5 to the 7th. This log base 5 and this base 5 cancel each other out because logarithms and exponents are inverses of each other, essentially just leaving us with a 7. So c here would be 7. Shortcut way, long way, arrive at the same answer. Something very similar is going to happen in question 16. Here we start with a 12 log base 12 of 34. We'll say equals c. So if this were an exponential, well, this is an exponential, we would have a equals b to the c. Don't be confused by the fact that we've got multiple c's floating around here. I can't help what variables they choose in their problems. This is not the same c. So if we wanted to convert this into a logarithm, we would rewrite it as log base b of a equals c, log back. So that would give us log base 12 of c equals this, which is log base 12 of 34. Well, if log base 12 of c equals log base 12 of 34, then necessarily c has to equal 34. The shortcut way of solving this same exact problem is if you start with 12 to the exponent of log base 12 of 34, the 12 base and the log base 12 cancel each other out because they're inverses, so we end up simply with 34. The shortcut way is really nice. Once you understand how it works and you can use it comfortably, I highly recommend using the shortcut. Question 27 is asking us simply to convert something from an exponential form into a logarithmic form. So our exponential form is 3 equals 243 to the 1/5 power. So this is our a equals b to the c. If we were to convert this into a logarithm, it would give us log base b of a equals c, so log back. Log base b would be log base 243. A is 3 and c is 1/5. So this is how it would convert. Log base 243 of 3 equals 1/5. So they want us to write it in this form. My variables and their variables don't exactly match up. So what they're calling a is the base. So a would be 243. What they're calling b, we have a 3 in that position. And what they're calling c, we have a 1/5 there. So those are the 3 values that you get when you convert. Question 5 is asking us to do something similar but in sort of the reverse direction. So we're starting with log base b, capital B, of 243 equals 5. Well, this is our log back. And if we wanted to convert this into an exponential, it would convert into a equals b to the c. Well, a is 243. B is capital B, that's what they called it, capital B, and C is 5, so the exponent would be 5. So we would have 243 equals capital B to the 5th power. That's what we would get if we converted this into an exponential. So they're calling 243, they're calling that C. Their base, they're calling B, which is here, it's an A, so what they're calling a is capital B. I don't know what their deal is with all these variables. And finally, their exponent is an f. Ours is a 5, so we would put 5 in for f. I think the hardest part of these problems is just going to be figuring out exactly what they're referring to with each one of their variables. Finally, they ask us to actually evaluate the expression. So we're looking for a b. We're looking to solve for b. So since b is not by itself on one side, instead of b we have b to the 5th power, we have to do the inverse of the 5th power, which is the 5th root. So we take the 5th root of both sides, and I didn't leave myself a lot of space to write this. We get the 5th root of 243 is equal to b, and you can use your calculator or maybe even calculate this in your head. We're looking for a number that multiplies to itself 5 times to give us 243. That would be 3. So that's where you get your evaluated answer. Question 15 is very similar to the examples we've done so far, but we're going to have to evaluate this one as well. So we're going to start with log base 4 of 1 over 4096 is equal to c, and we want to actually solve for c, or evaluate c. Since we already have c by itself on one side, there's really no more manipulation or inverses or changing things around that we need to do to find c. What we're looking at here on the left is simply an expression that we can plug into a calculator. Here's the deal. Our graphing calculators, if you have like a TI-84, TI-89, they don't deal well with log base numbers. Here is how you have to solve these. It's pretty strange the way you have to punch them into your calculator. We would plug in log of 1 over 4096 divided by log of 4. That's how you punch this into your calculator. And it's tricky too because you have to remember your parentheses. You've got to make sure that you're dividing the base. So the log of 4, which is the base, goes on the bottom of the fraction. So it's log of 1 divided by 4096 over log of 4. So we're going to have fractions inside of fractions here. These are not necessarily easy things to punch into your calculator, but this is probably the most efficient way to solve for C. And if you plug this into your calculator, you should get -6. So keep this in mind. This will be a lifesaver on problems like these. There is a way to solve this without a calculator, but it requires some mental gymnastics. So let's revisit this problem again. If we have log base 4 of 1 over 4096 equals C, we could convert this into an exponential. So this would be log back, B, A, C. And we convert this into an exponential as A equals B to the C. We have to figure out what value C is equal to convert 4 into a 1 over 4096. Now remember, if an exponent is negative, it's going to flip your number upside down. So that's exactly what's going to happen here. So we know that C has to be a negative number because that's going to turn our 4 into a 1/4. And then we have to figure out what power we would take this 4 to turn it into a 4096. And you could kind of mess around with your calculator there. The answer would be 6. So 1 over 4 to the 6th would get you 1 over 4096. So C would have to be -6 in order to make that happen. So you can approach this either kind of in the forward direction or the backward direction, depending on whether you're a fan of using your calculator to solve a problem, or whether you'd rather actually think through the problem and try to use logic to get to your answer. Either way, they are both very valid approaches. Let's talk about the meat of this unit. What we're really going to be wanting to do, and the reason we just talked about logarithms and we're introducing this topic, is because generally we're trying to solve for x in a function that involves logarithms or exponentials. That's at the heart of this lesson, is how do we solve for x when x is living somewhere inside an exponential or a logarithm. So in question 7, we are going to introduce kind of a new topic. So think about this. If I had 4x equals 7, we did an example like this earlier, and I want to, quote, get x by itself, we can divide both sides by 4. This is the act of taking the inverse to isolate x. That's exactly what we're going to be doing. But instead of taking the inverse using multiplication or division or addition or subtraction, we're going to be taking the inverse of logarithms, which is exponentials, or we're going to be taking the inverse of exponentials, which is logarithms. So here's an important note for you. You might want to highlight this. To undo a logarithm, you can make both sides into an exponential. To undo an exponential, you can take the logarithm of both sides. So these are inverses of each other, logarithms and exponentials, and we can use them to solve problems. So in example 7, we have log base x of 34 equals 1. It's going to be very difficult to solve for x when it's living inside as a base to this logarithm. So what we're going to do is I'm going to rewrite this to give myself a little bit more space, equals 1. We are going to take x to the power on both sides. So remember we talked about if we have the same base taken to two different exponents, those exponents have to be equal to each other. Well, we already knew that these two things were equal to each other. So if we take x to both sides, these two things are still equal. The left-hand side is equal to the right-hand side. We still have a balanced equation. Why did I choose x? I specifically chose x because now this x base and this log base x cancel each other out. So this all goes away. And on the left-hand side now we have 34. And on the right-hand side we have x to the first power. Well, x to the first power is just x. So essentially we got our log base x to cancel out by taking x to the power of both sides. And that's how you undo a logarithm. And it's a pretty easy and simple and straightforward process that lets you arrive at a fairly quick answer. So we're going to get plenty more practice in question 8. Question 8 is giving us a generic formula for a function. They're saying, okay, we have f of x equals a to the x, and we're going to treat each one of these rows like a completely separate problem. In the first row, they're saying, okay, I'm actually going to give these all numbers. We're going to call this number 1, number 2, number 3, number 4, number 5, and number 6. That way, don't get confused when I write all my notes out. So for number 1, we're going to say, okay, a is equal to 2, x is unknown, and f of x is 1/4. Solve for x. Well, the way we can solve for x, I need to get better about leaving myself some space. The way we can solve for x in this problem is by essentially undoing this 2. Well, the opposite of an exponential is a logarithm. So what we would need to do is take log base 2 of both sides. And that's how you get these two things to cancel, leaving you simply with an x on the right-hand side. And on the left-hand side, you have log base 2 of 1/4. So we know what x is equal to, but I don't know if web class wants you to type your answer like this. Probably not. I'm pretty sure they want us to simplify our answer, so we need to plug this into our calculator. The way we type this into a calculator is log of 1/4 divided by log of 2. So punch that into your calculator. You end up with, actually, probably something pretty nice. Log. Yeah, you get -2. So x here would be -2. That was part 1. We've got many more to go. Part 2 is starting you off with a totally different set of values. So we have f of x equals a to the x still, but this time a is equal to 3, x is equal to 4, and f of x is unknown. Well, this one's pretty easy. To find f of x, we just take 3 to the 4th power, which is 81. So we'll plug in 81 as our answer right there. For number 3, we have a is 3, x is unknown, and f of x is 9. If we want to solve for x in this problem, we have to undo this 3. We do that by taking log base 3 of both sides. Log base 3, log base 3. So on the right-hand side, the log base 3 of 3 are going to cancel each other out, leaving us with just an x on the right. Then on the left, we have log base 3 of 9. We can plug this into our calculator. You just plug in log of 9 over log of 3, which should give us 2. Let me type it in and double check. Log of 9 divided by log of 3 gives us 2. And this problem was probably pretty easy for us to figure out from the very, very beginning. I mean, if you start out with 3 to the x equals 9, well, it's 3 squared that equals 9. Most of us can do that in our heads, so we probably pretty early on could have figured out that our x value had to be a 2. But I'm just showing you the formal step-by-step way that we would solve these problems. All right, number 4. Number 4, they give us f of x is 2, a is 4, and x is unknown. So we have to solve for x. And this is another one that you could probably do in your head, but we will actually write it out algebraically just for good measure. So to get that x by itself on the right, we have to get rid of that base 4. We cancel that out by taking log base 4 of both sides. Log base 4. So we end up with log base 4 of 2 equals, these cancel, and we just have x over here now. So you can punch this into your calculator as log 2 divided by log 4. And that's going to be equal to 1/2. Let's see, log 2. I'm punching this into my calculator just to double check myself. Log 4. Yeah, that gives us 1/2. So x here would be 1/2. All right, number 5. In number 5, our f of x value is unknown. Our a value is 16, and our x value is 1/2. So this one's going to be pretty easy to calculate as well. You can use a calculator, or most of us know that 16 to the 1/2 power is the same as the square root of 16. So that would mean that f of x is equal to 4. And last one, number 6. We start out with our f of x is 1/5. Our a value is unknown, and our x value is -1. So again, this is another problem that we can probably solve just by looking at it. What to the negative first power would be equal to 1/5? A should be 5 here, but let me show you how to solve it algebraically. Probably the easiest way to solve this algebraically would be to rewrite the 1/5. 1/5 is the same as 5 to the -1. And on the right, we have a to the -1. Well, if these two sides are equal to each other, then necessarily 5 has to be equal to a. So a is 5 in this situation. Just a few examples of how you might solve when you have different pieces of your functions missing. Example 9 is very similar to the one we just did, except for this time our function starts us off with a logarithmic function. So we've got f of x equals log base a of x. So let's just do a few of these. We're not going to do all of them. Let's do maybe the first and the second and one of the last ones. So we'll make this our third one. So for our first problem, we are given an a value. So we've got log base 4. We are not given an x value, so that's an unknown, but our f of x value is -3. If we want to solve this equation for x, we're going to need to get rid of this log base 4. The way we get rid of log base 4 is you do its inverse. We are going to take 4 to the power of both sides. So that would be 4 to the -3 equals this base 4 to the log base 4 are going to cancel each other out, leaving us with just an x. So you could punch this into a calculator, or you could do it in your head. This is going to be equal to 1/64. For number 2, we are given an f of x value of 2. We are not given an a value, but we are given an x value, 25. So in order to solve for a, I'm not going to be able to do that while it's sitting here as the base of my logarithm. So we're going to need to find a way to eliminate this log base a. And it'll work very similar to the last example. We're going to take a to the power of both sides. So on the left, that'll give us a squared. And on the right, the a and the log base a cancel each other out, leaving us with 25. And this one should be pretty easy for us to solve. A squared equals 25 means that a has to be 5. Or you could think about this as you could take the square root of both sides, take the square root, and you end up with a equals 5. The last one I want to do from this example is starting us off without an f of x. There's no f of x here. Instead, we start off with just an a, so log base 2, and an x, 1/4 power. This is something we can plug into our calculator. We would type it in this way: log of 1/4 over log of 2. You would need parentheses around this when you punch it in, so be careful of that. So I'm going to punch that into my calculator real quick. Log 1/4 divided by log of 2, and that gives me f of x equals -2. So I trust that you'll be able to solve the rest of these on your own, or at least similar problems like these. Question 21 is exactly like the one we just did, so I'm going to go ahead and skip that one as well, and that is the last example we're going to do in this video. So I hope this helps you understand generally what logarithms are and some of the rules we're going to use to solve problems involving logarithms and exponentials.